In this video, I'll be discussing the process of finding the limiting reactant for a reaction, and also the process for predicting the number of products that are formed based on two different reactants that you're given. And so how this process is different than a lot of the stoichiometry problems that we've done before is that, typically speaking, I've given you the amount of one thing in the chemical reaction, and we've just assumed that you had the right amount of other stuff so that whatever you had of that first thing, it all got used up. But in this case, when we have a limiting reactant, what I'm going to do is I'm going to give you the amounts of two of the reactants. One of them is going to be limiting, one of them is going to be excess, and then you have to determine how much of the reaction actually takes place. To help you understand this concept, I'm going to give you a bit of an analogy here. So imagine here we have some different bike parts. We've got the frame for the bike, and we've got these two different tires. All right. As it stands, you could currently make one bicycle because you've got one frame and you've got two tires. Now let's say that you had some more tires here, right? Let's say now we have, instead of two tires, we have 6 tires. The question becomes, how many bikes can we make? Well, if we have just one frame, it doesn't matter that we have 6 tires because we can still just only make one bike. So one frame and 6 tires, we can still only make one bike. And so here's how this analogy goes. We've got an excess of tires, meaning we have lots of extra tires, all right, but we are limited by the number of frames that we have because the number of frames that we have limits us to being able to make one bicycle. Now let's say we got more frames here, all right? Now we can make 2 bikes, and now we can make 3, all right? But once I get my 4th frame here, we can still only make 3 bikes because we've got 6 tires. All right, 6 tires is enough to make 3 bikes. Despite the fact that I've got 4 frames, all right, I can still only make 3 bikes. In this case, I'm limited by the number of tires that I have, and I have excess frames. All right. So to get into the vocabulary then of this section, I say that the limiting reactant is the reactant that you're going to run out of first. If you just don't correctly mix things together, you're just grabbing some amount of your 2 reactants and mixing them together, it's not in the correct proportions, then one of your reactants you're going to run out of first. That is called your limiting reactant. And then one of the reactants you'll have extra of, and we call that your excess reactant. There are 2 different things that we have you do in this worksheet. The first one is just identifying which of the reactants is limiting. To do that, you follow this process where you write out the balanced chemical equation, and then you convert both of the starting masses into moles of the product. All right, and then whichever one creates the smallest number of moles, that is the one that we go with as the limiting reactant. And I'll go through an example, and hopefully after I go through one of these examples, that will make more sense. All right, so I'm going to go through actually and do that process now. So the first thing I'll tell you about this process is that you need to write small because you got to get 2 of these stoichiometry problems into one little tiny space on your paper. And so make sure that you write very, very small as you're going through this. This first problem says identify the limiting reactant when 45 grams of O2 reacts with 42.3 grams of H2 to produce water. So step number 1, we need to write and balance the chemical equation. So what we've got here is we've got H2 reacting with O2 to produce water. All right, so we've written our chemical equation. The next thing we need to do is we need to balance it. So to balance it, I'm going to put a 2 here and a 2 here. Okay. And then the next thing we're going to do is we're going to convert each of these masses that we were given in the beginning to moles of one of the products. In this case, there's only one product, is water, so we'll convert from grams of our starting materials to moles of water. So to start off with here, I'll also need actually 2 molar masses in this because I need to go from grams to moles for oxygen, and I also need to go from grams to moles for hydrogen. And so I know that O2, if you look up its mass on the periodic table, that's 2 times 16, which is 32.00 grams. And then H2, if you look up its mass on the periodic table to get the molar mass, it's 2 times 1.01, which gives you 2.02 grams. So then we start here, 45.0 grams of oxygen, 45.0 grams of oxygen. And so we want to get it out of grams of oxygen, so out of grams of O2, and into moles of O2. And then we want to get it out of moles of O2, and we want to get it into moles of H2O. Conversion factor is grams to moles. That's 32.00 grams in 1 mole, so 32.00 grams in 1 mole. And then to do mole to mole, we're looking at the coefficients here. The coefficient in the balanced chemical equation on oxygen is 1. The coefficient on water is 2, so it's a 2-to-1 ratio. And then we go through and we calculate that, round to the correct number of sig figs. You should get 2.81 moles of H2O produced. Okay, so what this says is we have enough oxygen to make 2.81 moles of H2O. Now we're going to go with hydrogen. Hydrogen, we've got 42.3 grams of H2. All right. In a similar process, we want to cancel out grams of H2 and get it into moles of H2. All right, and then we want to cancel out moles of H2 and get it into moles of water. Conversion factor is grams to moles. That's the molar mass, which is 2.02 grams per 1 mole for hydrogen. And then the mole-to-mole ratio, looking at the coefficients, it's 2 moles of hydrogen per 2 moles of water from that balanced chemical equation. And so if you go through and do that math, you get 20.9 moles of water produced. Okay, and so again, summarizing what's happening here, we have enough oxygen to make 2.81 moles of water. We have enough hydrogen to make 20.9 moles of water. All right, and so what we have here is we have a limiting reactant of oxygen. So we know that oxygen, or O2, is limiting because it limits how much we make. We're actually, in the end, only going to make 2.81 moles of water. It's that whole situation of if you have enough frames to make 5 bikes, but you only have enough tires to make 2 bikes, you're only going to make 2 bikes. All right? You go with the smaller number. All right? We have enough hydrogen to make a whole lot of water, 20.9 moles of water. But we only have enough oxygen to make 2.81 moles of water, so we only make 2.81 moles of water. Oxygen is limiting, hydrogen is excess. That's how this one works. To go through another example of this, I've got this reaction with MgOH2 and HCl. They come together and it says that they form MgCl2 in water. So then we need to go through and we need to balance this. To balance it, you end up with a 2 here in front of HCl, and you end up with a 2 in front of water, and then it should be good. All right, and then again, what we do is we start with the grams that we're given, and we need to convert to moles of water. So we need molar masses, in this case, for MgOH2, and we need a molar mass for HCl. So if you calculate the molar mass from the periodic table for MgOH2, you should get a molar mass of 58.33 grams. If you calculate the mole for HCl, or the molar mass for HCl, you should get 36.46 grams. So we start with 80.5 grams. Of MgOH2. Then we need to go from grams to moles, so we're going to use that molar mass. We know that there are 58.33 grams of MgOH2 in 1 mole of MgOH2. All right, and then looking at the balanced chemical equation, we know that for every 1 mole of MgOH2 we can choose now either one of our products, actually, so this is something important to mention. We could go to MgCl2 or H2O. I'm just going to choose H2O. You could have chosen MgCl2, though. You would have gotten the same final answer. The math would have worked out slightly differently, but you would get the same answer in the end in terms of what reactant is limiting. But I'm going to go to H2O, so we're going to say there are 2 moles of H2O. So you just choose one of your products and go to that. It doesn't matter which one. All right, so if you calculate that, you should get 2.76 moles of water. Oops, moles of water. Okay, so now we're going to start with HCl instead, that other reactant that we're given. So we've got 25.6 grams of HCl. We know that there are 36.46 grams of HCl for every 1 mole of HCl. And then also we know that there are 2 moles of HCl. And because we chose water in the first one, we have to use water again. So we're going to say there are 2 moles of water. Go through and do that math, and you should get 0.702 moles of water. Okay, so again, to summarize this process, we have enough magnesium hydroxide to make 2.76 moles of water. We have enough HCl to make 0.702 moles of water. So we're actually going to make 0.702 moles of water because we go with the smaller amount. And that means that in this case, HCl is limiting. Okay, on the back of this sheet, there's a slightly different process. What we're going to be doing is we're going to be seeing how much of one of the products we make. And so basically what we're going to do is we're going to take each of these conversions, each of these stoichiometry problems one step further, and we're going to try and see how much of the products we can make. And starting with the 2 reactants, we'll convert to products. We'll get 2 different numbers. Again, we're going to go with the smaller number because that's how much we can actually make. So this one here, it says we start with 25.2 grams of chromium, and it's with 9.56 grams of Cl2, and we're asking what mass of CrCl3 are we going to produce. So the first step, again, is to find a balanced chemical equation. So we start with Cr and Cl2, and it makes CrCl3. We have to balance this. It's not too bad. We end up with 2, 3, and 2 as our coefficients. Now we need a lot of molar masses in this one from the periodic table because we need the amount of chromium and the molar mass of chromium and the molar mass of Cl2 because those are the 2 reactants that we start with. But we're going to try and get into mass of CrCl3 in the end, so we also need the molar mass of that. So these 3 molar masses, if you've got chromium, the molar mass from the periodic table is 52.00 grams. For Cl2, that's 2 chlorines. The molar mass is 70.90 grams. And for CrCl3, adding up the masses there from the periodic table, you get 158.35 grams. All right, so those are our 3 molar masses that we're going to be dealing with, and you'll see how those come into play in this process. And then again, I said it's very similar to what we were just doing. So you're going to start with 9.56 grams of Cl2. And then you're going to convert from grams of Cl2 to moles of Cl2. Then we're going to go from moles of Cl2 to moles of CrCl3. And then this is where we go one further step. We don't want moles of CrCl3 in the end. We want to know how many grams of CrCl3. So we go from moles of CrCl3 to grams of CrCl3. The conversion factors, grams to moles, we've got the molar mass. So for chlorine, it's 70.9 grams, 70.90 grams in 1 mole. Mole to mole ratio for Cl2 and CrCl3, we look at the balanced chemical equation. It's a 3:2 ratio. All right, and then on the next one, we know that 1 mole of CrCl3 is 158.35 grams. If you go through and do that calculation, you should get 14.2 grams of CrCl3 produced. All right, but we need to do it again now. We need to do it starting with 25.2 grams of chromium. So we start here, 25.2 grams of chromium. And then we need to go from grams of chromium, so we know there's 52.00 grams of chromium in 1 mole of chromium. And then we go from moles of chromium to moles of CrCl3. So there are 2 moles of chromium from the coefficients for every 2 moles of CrCl3. And then lastly, again, we go from moles of CrCl3 to mass of CrCl3, so 158.35 again. And we can calculate how many moles, or how many grams we could create there. We get 76.7 grams. Okay. And so on this one, again, this is the thinking that happens at the end. We have enough chlorine to make 14.2 grams of CrCl3. We have enough chromium to make 76.7 grams of CrCl3. That means in reality, we can only make 14.2 grams of CrCl3. This other one is not going to happen, all right? Because once we run out of chlorine, once we run out of that Cl2, we're not making any more CrCl3. It doesn't matter that we have extra chromium or that we have enough chromium to make more of the CrCl3. So we go with a smaller number. Okay, and just one last example of this. In this one, we're starting with S8, which is some elemental sulfur, plus O2, and it creates SO2. Balancing this one isn't too bad either. We just end up with an 8 there, and an 8 in front of O2, and things are good. We need 3 molar masses again for this, 1 for each of the reactants that we're starting with, and 1 for the product. So the molar masses for these are, for S8, we get 256.56. For O2, it's 32.00 grams. And for SO2, it's 64.07 grams. Okay, now we're going to do our 2 stoichiometry problems. On the first one, I'll start off here. It doesn't matter which one we do first, but I'll do 650, and that point means it's 3 sig figs, so 650 grams of S8. And then we're going to go from grams to moles for S8, so we use the molar mass. There's 256.56 grams of S8. in 1 mole of S8. All right, then we're going to use the coefficients to get from moles of S8 to moles of SO2. So there's 1 mole of S8 for every 8 moles of SO2 that we produce. And then as a last step, we need to get from moles of SO2 to grams of SO2, so we're going to use that molar mass for SO2. We know that in 1 mole of SO2, that it is 64.07 grams of SO2. Go through and do that entire process, and what you get is 1,300 grams of SO2 produced. Now in this one it's interesting because it should have 3 significant figures, but it rounds right to 1,300. So I'm going to put that little overline or overbar above that 10 to indicate that that one is significant. So as the second step here, we need to start with the other mass, that 200 grams of oxygen. And again, this is 200 point, indicating that those 2 zeros are significant zeros. And we've got grams of O2. We're going to go from grams of O2 to moles of O2, which is the molar mass. So we've got 32.00 grams in 1 mole. All right, then we go from moles of O2 to moles of SO2. That's 8 moles of O2 in 8 moles of SO2 coming from the coefficients on the balanced chemical equation. And then we're going to go from moles to grams for SO2. So we know that in 1 mole of SO2, there's 64.07 grams of SO2. Multiply all of that out, and we get 400. All right, and we need 3 sig figs, so I'm going to call it 400 point grams of SO2. So what this is saying is that we have enough S8 to make 1,300 grams of SO2. We have enough oxygen to make 400 grams of SO2. So what we're going to do here is we're going to end up making 400 grams of SO2 because we can only make the smaller amount, and then we run out of oxygen. We have extra S8 that we don't end up using up, all right? And that's how this process works. So you've seen a couple examples here of each of these types of problems. They work out exactly the same way every time. If I ask you to identify the limiting reactant, you only have to go to moles. But if I ask you to determine how much of one of the products is produced, then you have to go all the way to grams for that product. All right, you select the smaller amount, and whichever reactant created that smaller amount is the limiting reactant. There are some more practice problems on your worksheet for this. I encourage you to check those answers with the key that's been posted online. And if you have any questions on any of that, make sure that you come in and ask.